find this. I swore that ortho, meta, and para directing effects was in that.
So this video.
That's okay. We'll discuss it. It's not a problem. It may be in a different video that's on the playlist. I'll find it. But anyway, let's go to the next reaction right here. Right, this Friedel-Crafts alkylation. All right. If you alkylate the benzene ring, what am I adding to it? What does the alkyl part mean? Right, isn't that like any type of carbon chain? It can be a 5-member carbon chain. It can be a CH3. It can be whatever. Right, this will always be some type of halide, some type of alkyl halide. So you'll take your benzene ring plus an alkyl halide. Right, and then in this case, the mechanism is a little bit different. And then your catalyst is also different, right? In this case, your catalyst is aluminum trichloride. And so you'll see for Friedel-Crafts alkylation and acylation, your catalyst is aluminum, right? But let's talk about the alkylation right quick. Right, so here's I'm just gonna do the same ring. And let's do I wanna do a different. All right, let's do this compound, all right? Because I want to talk about one of the drawbacks of doing Friedel-Crafts alkylation, right? So what you would expect, and you're doing this in the presence of aluminum trichloride, what you would expect is this.
Are you drawing something?
I can't see your screen.
All right, relax. Come on. All right. What about now?
No.
No. No.
All right, hold up.
Your cursor is frozen.
I told you my computer's been acting real stupid lately. Yeah. But I don't want to get another one because it's too much hassle.
Okay, we can now.
Yes.
Yes.
All right. So with the Friedel-Crafts alkylation, let me just put that here. Right, I'm adding the alkyl halide to my ring. And so with this particular reaction, I would expect to get, let me move this so I'll have room to draw the chain out. I would expect this as my product. So this is the primary right here. Right, I expect this as my product. Is that right? I expect this carbon right here to end up attached to the ring. Same carbon right here. Yes or no? And the reason it looks weird is because it's just turned over.
Yeah. Yes.
I expect that because, again, it's a substitution. I'm taking one hydrogen off the ring and replacing it with whatever is attached to the halogen here. Everything, not just that carbon, but the whole piece, right? And so that's expected, but what I get is something different. And this is a drawback for using Friedel-Crafts alkylation. There's a lot of other methods that you can use that will be better than using this. What I get is this. Right, where instead of attaching at the primary carbon, it ends up attached at the tertiary carbon. All right, can y'all see that? Anybody not see it?
I don't see that.
So
Same. I don't either.
so this carbon right here is the carbon that's bound right here. Let me make sure I got enough carbons attached to it. 1, 2, 3. Yeah. Right, because all of these are carbons. Let me zoom in some. All of these are carbons in this chain.
Oh, I think what's confusing me is where did the chlorine go?
Right. Well, the chlorine is gone, right? Because this is the product.
Right.
Yeah. So the chlorine is gone. So we'll have something like this: HCl plus AlCl3. Because you always regenerate the catalyst. You never use that up.
Okay.
Right. So let's go through the mechanism and then it'll make sense. Right. So let's do that. So what's the first step?
To prep.
Prep the electrophile. So if this is my electrophile, I'm gonna draw it. I'm gonna turn it around. If that's my electrophile, is that right? Is it the same? Did I add an extra carbon on the end?
It looked like an extra carbon.
Yeah. Yeah, I think we got it now. All right, so that's my electrophile, and then I'm gonna treat this with aluminum trichloride. In this case, you don't make a complex, right? You actually end up pulling off the halogen. Right, so it does coordinate to aluminum, but you end up pulling off the halogen. All right, so what you end up with in that case is aluminum tetrachloride, which is now negative, and then you end up with a primary carbocation. Is that bad or good?
Bad.
Was that you, Jalen?
Yeah.
It's bad, right?
Yeah.
So how do we fix that?
Resonance.
Right, because under normal circumstances, that's what you expect the ring to attack. But that's too unstable. So did you say resonance?
Well, no,
Is
there's
there
no
something else
double
we can do?
blind. So, the shift, a hydron shift.
We can do a hydride shift. What's the purpose of that? Every time we've seen that hydride shift, why did that happen?
To make it more stable.
To go from a less stable cation to a more stable cation. So I need to zoom on that so I can actually show the arrow or fit it in there. Right, so this hydrogen is going to shift down to here, the hydrogen and its electrons, right? And that's going to give me this as my new cation. Anybody disagree or not see it? Yes, no,
See it.
don't care. Monday.
We see it.
Say that. Just say, yeah, it's Monday.
No, I said I see it.
Okay, all right. So this is now the electrophile that's going to go into the second step. All right. And the reason why it's tertiary again is because when you pull off the chlorine, you make a primary cation, which is bad, and that primary cation rearranges to give you a tertiary cation. She down me. So now what happens in the second step?
It gets attacked.
The ring is going to attack. Right, so here's my ring. I'm going to keep that the same. And now here's my cation. Can you see it now? Like we have it drawn up there, up top. Is it making more sense now?
Mm-hmm.
Like we had it drawn here. Right, so the ring is going to attack this. Same type of intermediate with a plus charge on that carbon. And then the third step would be to do what?
Go back to
The chlorine.
Reestablish the aromaticity.
Mm-hmm.
Yeah.
We establish aromaticity. How we gonna do that? Do we do it we do it
Chlorine
the way we
for
did the last
hydro-
time? Say that again.
Deprotonation.
Use
Go-
the for a hydride shift.
Somebody was breaking up. I heard somebody say something about a hydride shift.
Use
It
the
wouldn't-
chlorine for the hydride shift.
Well, in this case, this
it
is
wouldn't be a hot drive shift. Wouldn't it just be
it'd be
chlorine
proton.
going to attack?
It's deprotonation.
Yeah,
Yeah.
you have to deprotonate with the aluminum, right? But it's not a hydride shift. It's actually a proton transfer. That's two different things. But I understand what you were saying though. So that's going to attack there. This pair of electrons is coming here, right? And then my product, I'll get this. Plus what?
HCl.
Mm-hmm. And then I always, anytime you use a catalyst in a reaction, you always get it back at the end of the reaction. It always regenerates so it can go and do that reaction again.
Okay.
Yeah, you never use that catalyst up. Now it might at some point die and stop working, but that's after several iterations of the reaction. It can just keep going and keep going and keep going until it basically gets tired, and then it'll stop working. But at the end of every reaction, you always get the catalyst back. If you start with a catalyst, at the end of the reaction, it's going to be regenerated. Right? Any questions about that? So this rearrangement is one of the drawbacks of this Friedel-Crafts alkylation. I'm gonna put that here. But like I said, there's a lot of different ways that you can add an alkyl group to an aromatic ring without using this method. It's kind of antiquated. There's so many different coupling methods that transition metal catalyzed couplings that people don't really use this anymore.
Can you yeah, thank you.
Yeah, I zoomed in so I could write. It's hard to write coherently, even though it's still chicken scratch. It's hard to write when it's zoomed out.
Thank you.
Oh, let me get all of that. All right. Any questions? Any other questions about the alkylation or the halogenation?